Hey everyone. Yes, so thanks for the introduction. I'm going to be talking about a system that we have developed at the SRI lab at ETH Zurich called Debin, and this system is using machine learning to recover the debug information in stripped binaries. So this system came out of the work of Jing Swan, who was a master's student at the time. Now he's a PhD student at the SRI lab. Unfortunately, his visa got delayed, so hence I will be presenting this talk today. All right, so binaries, let me just first give you an example of why debug symbols are pretty useful in the case of reverse engineering. So here, for example, typically if you have a binary, you would have the code section, with all the assembly, and then you would also have the debug symbols that will define, for example, the names, the types of the high-level information that comes from the source code. And many of the reverse engineering tools that we use today, they have a way to leverage this information to help the security engineer. For example, if you take Hexrace, which is a popular tool that can decompile the code, you would get pretty readable pseudocodes to understand what the binary is actually doing. So for example, you get descriptive name of functions, variables, and so on. And the problem is that typically in practice, you would remove the debug symbol. This can be either to optimize the binary to make it smaller. Sometimes you would want to prevent people from understanding what your binary is doing. And in particular, if you look at malware, typically you always remove the debug symbols for obvious reasons. And then suddenly these tools become less useful because they cannot pick up interesting semantic information about the code to help the people to work on that, to understand what's going on. So the question that we address in this work is, well, can we somehow recover the debug information that was removed? And at least intuitively, this seems like a pretty impossible thing because once it's gone, how would you know what was there? However, it turns out that we can, with pretty high accuracy, recover the information. In fact, we do it I'll show you the results for different architectures with roughly 65% accuracy, which is pretty useful because this means the majority of the information we can put back there. So let me quickly tell you. So there's actually some prior work on applying machine learning for predicting deobfuscating programs. This has been done, for example, for JavaScript, for Android applications. But binaries pose a different challenge because the representation is really low level and really lots of semantic important information is lost in the compilation. So here, for example, you see the assembly code for code snippet that computes the sum of the first n natural numbers. And the first thing that you don't know is you don't even know which registers and memory offsets here correspond to semantic variables that were present in the source code. For example, if we had the source code, we would actually know that here I highlight the registers and offsets that correspond to something semantic. However, some of the registers are just introduced for temporary computations. So these are just things introduced by the compiler itself. The other challenge is that we don't have the names, we don't have the types of these variables. For example, if we had the debug symbols, we would know that the highlighted in red EAX register is actually stores the result of the computation. It's an integer variable. Sometimes you would also have multiple registers and offsets that represent the same high-level variable from the source code. For instance, here we have the ESP and ETX are storing the value of unsigned integer n. And this information is also gone. So what we build with this system is we start with the stripped binary without debug symbols, and then the Debin system, given this, recovers the location information. So here in different colors, I highlight how Debin recovers at which places are stored the same variables, and then it also infers the names and the types of the types of these variables. So next, I wanted to quickly show you a small demo just so you can see how it looks. The system is actually publicly this doesn't show. There we go. I think that would work. So the system is publicly available at debin.ai, and you can upload any binary here to the interface. And now I'll just click on one of the samples to show you what happens. Zoom a little bit. So in the prediction results, zoom a bit more. All right, that's good. So it would recover 3 of the important sections in the debug symbols. For instance, in the sim tab, it would recover at which offset what kind of code is represented. So this is an offset in the code section. And then it says that it's a function. It would predict correctly the name of this function. And then it has other kind of information. So in the debug symbols table, for example, it would identify all the variables. It would give a name to these variables. It would say what's the location that corresponds to this variable. And then you can look up in the debug location exactly what this is. So the idea is not to use this kind of information when you do reverse engineering, but this is the kind of information that debugging and reverse engineering tools would pick up and use to help understanding what the binary does. Okay, so next I'll give you a high-level overview of how Debin achieves this. And so it's based on machine learning. And the idea first is to learn from a lot of binaries that do have the debugging symbols in them to understand what, to capture kind of this information. So the learning phase proceeds in 2 phases. In the first phase, Debin would extract features for about all the offsets and registers, and then would predict which one of those corresponds to semantic variables at the source code level. So it would construct this variable recovery model. And then as a second phase, it would construct, I will explain this, it would construct different relationships between the registers, instructions, and constants in the code. And based on this, it would learn how names and types are associated to these variables. Having trained these 2 models, then they're used in the prediction phase to recover the debug symbol. So that's what I showed in the demo, starting from the street binary. First, it would get all the registers, memory offsets, and figure out which ones have semantic meaning. Then it would assign names and types to those that are supposed to have some semantic meaning. And finally, based on this information, it would reconstruct the debug symbols in the binary. So next, I will give you just the key points on how these 2 phases work, and then I'll move to some results. Okay, so in the first phase of the prediction is to recover the semantic variables in the binary. And the learning here proceeds by learning from a lot of binaries with debug symbols. For our experiments in the debug system, we used about over 8,000 binaries with debug symbols. And we also defined many different feature templates. So these templates capture different semantic information about what the registers do. So things like what operations are invoked on them, what other registers depend on them, and so on. Then, based on this, it would analyze the binaries and it would extract different features based on the templates from using the binaries with debug symbols. So in the evaluation, so we had over 10,000 such distinct features. Then it would transform those into binary vectors, because at this point we know all the features we have observed in the training data. And then it would train a lot of, it would train 100 decision trees that aim to classify, so given a register and these features, does it have any semantic meaning at the source or not? So that's the learning phase. Then, at prediction time, what it would do is for each register, it would first extract the features, again, by looking at the assembly and looking at things like what instructions are used and what dependencies they are. For instance, here, we're incrementing the EDX register. So it would say that we're doing EDX plus 1. We would convert this to a feature vector and then do the prediction using all the decision trees. And here the model that we're using is extremely randomized trees, which means that we would apply the feature vector on all the 100 decision trees and take the majority of the vote as the actual classification, the final classification. So this is prior work. I have put a reference there for whoever is interested to look at. So as outputs, it's a binary classifier. It says whether it's semantic or it is a register that is just used for some intermediate computation. All right, so once this is done, the next phase is to predict the names and the types of the semantic variables in the code. And for this part, Debin uses a probabilistic graphical model. Let me give you some idea of what this is. So it's a graphical model, so it has a graph representation where the nodes in this graph are split into 2 kinds. So some of the nodes would be known. So in this case, we have a constant 1, which is a known element in the graph. And then it would also have unknown elements. For instance, we have 3 registers here that we don't know what their names and types are at this point. Okay, so the way these registers here, they're connected with edges, and these edges correspond, they represent different semantic meaning of how they are used in the binary. So the precise details on how these features are defined and derived is in the paper. We defined 23 such templates to represent the semantic information about the registers and the offsets. So the next important thing is that each of these edges between the registers is associated with different feature functions. And these feature functions, they define, for instance, the edge here between the top two registers, EDX3 and ECX1, defines that there's some condition not equal being executed on them. And then the different feature functions, they define concrete names that can be assigned to these registers. For instance, in the feature function F1 says that we can assign I to EDX3 and N to ECX1. And then it also assigns a weight that intuitively defines how likely this naming assignment is. And then this is, so we have these feature functions associated to all the individual edges. In addition, there are also factors in the graph. For example, here the constant 1 is linked to two other registers. So these factors are useful because you can connect multiple program, more than two program elements in some kind of relationship. So this is also pretty useful. So the key point here is that once we have defined all the feature functions and the weights, then we can find what is the most likely assignment for all the registers. So what should be their names, what should be their types, and this. Here, know that there is this interdependence on how we assign the name. So depending on what name we would pick for EDX3, this influences what values we would pick for some of the other registers. Okay, so the question is, well, how do we know what these feature functions are, and how do we learn their weights? And that's done during the learning phase, which again starts with a large data set with a lot of binaries that do have the debug symbols in there, and with different feature templates that define important semantic dependencies between the registers. So in the first step, we do the following. So first we extract all the program elements from the binaries. So here this includes things like registers, memory offsets, instructions, constants, and then we link them with the different feature functions that we have defined. So the actual graphs that you can construct from these binaries for real-world binaries, you get graphs with over 1,000 nodes, so they can get pretty huge. So then at the same excuse me. So then at the same time, we also use the templates to instantiate. From the templates we instantiate concrete feature functions. So again, these feature functions, they define the concrete names that can be assigned to the program elements. Okay, so that's at this point, we have extracted all the feature functions, but we still haven't assigned concrete weights that's associated to those. And this is done by training a model, where the point is to find weights for each of the feature functions and the different factors that would maximize that the training samples are predicted correctly. Okay. All right. So having trained these two models, now I want to show you a full end-to-end example on how this prediction would work. So we start with the stripped binary, where we only have the assembly code, no debug symbols at this point. First step, extract all the registers, the memory offsets, any known elements that are in the binary, and then we first run the first step of the prediction process, where we would classify the registers and the memory offsets into semantic or temporary variables. That would be that step, and then afterwards we take all the program elements, and then we construct this large dependency graph that captures how these program elements interact with one another. And then we do map inference, where the goal is to find the most likely assignments of names and types to the unknown nodes in this graph. So as I mentioned before, this is a dependence. It's a joint prediction. So you're predicting the names of all the things together, and this means that you don't always pick the highest possible thing according to each feature function, but sometimes you pick something that's less likely. So in this example, you would get the maximum, the most likely score if you select this feature function here for this particular edge. Okay, so having picked the correct names and types, these are plugged into the graph. And finally, it is used to reconstruct the debug, the sections in the debug symbols. And that will be our output. Okay, so for the concrete implementation, we use the binary analysis platform, which is a pretty popular framework for analysis of binaries. For the learning, we use several frameworks. So we use the scikit-learn framework to train the extremely randomized trees model. And then we use nice2predict for the structured prediction over the graphs. In terms of training data, we took 830 Linux packages, and we considered 3 different architectures so this approach is actually independent on what kind of architecture we're using. So we experimented with 3 different kinds to see if there's any variation on the accuracy that you would get across these different architectures. So we took x86, x64, and ARM architectures. And then we did the following evaluation. So I will show you what's the precision in the first step where we recover the variables, and also precision for the second step of the name and type prediction. And finally, I'll give you some examples of how useful the system is if you want to inspect some malware samples. Okay, so for the precision of the accuracy of the variable recovery, so we have the ground truth where we know exactly which program, which registers and memory offsets have semantic meaning and which ones are used for temporary computations. And when we run Debin, it would select some of those as semantic. So what we care here about is we care how many of the semantic things were correctly predicted. So we would take the number of correctly predicted program elements over the total number of program elements. And here we got a pretty consistent result across the 3 architectures. So the accuracy was roughly 90%. And this is important for the later stages, because if you mess up in inferring what has semantic meaning, the next phase would suffer from this mistake. Okay, in the next now we look at the name and type prediction. So here you have the total number of elements, and the circle identifies those elements that would be predicted name and type. For the dark red segment, these don't have semantic meaning, so there's no need actually for prediction. But the green segment, the dark green segment has we have the ground truth over those. Then for some of those, the black segment shows where the Debin would mispredict, would give basically the wrong name or type, and the dark green would identify those that have exactly the same type or name as it was in the original binary file. So we measured 3 different things. We measured the precision, which is the number of correctly predicted names and types over the total number of predicted things, program elements. And then recall covers the number of correctly predicted names and types over the ground truth of all correct names and types. And we also measure the F1 score for that captures the combined precision of both metrics. So here we also get pretty consistent results across the 3 architectures. So you see the precision and recall and F1 score for name, type, and overall. And in all cases, the precision and recall were roughly around 65%, which means majority of the elements were actually correctly predicted. Okay, so as a final note in the evaluation, I'll give you some idea of how this performs on malware samples. So here we don't have the ground truth because we don't have the source code of this malware, but we basically inspected the manual and tried to see what interesting things we can find there. And so in one of the cases, we saw malware that was manipulating the DNS settings. And then we saw that once you run the malware through Debin, it would actually correctly identify the DNS RFC that it's implementing. It would also capture that there's a loop over the entries in the DNS record and so on. So overall, this was helpful to understand what exactly this malware is doing. And there were a few other also useful examples. For instance, there was one malware that was opening a network connection and then sending sensitive data over this channel. So again, it correctly predicted the names for those functions. That's what made it easier to reach this conclusion that that's what's happening there. All right, so with this, I'm going to conclude. So as I mentioned, the system is publicly available at debin.ai. So feel free to give it a try and give us feedback. Thank you.
All right, as usual, we have time for questions, and please state your name and affiliation.
Hello, Johannes Kinder, Road Holloway, University of London. Fascinating talk. This is really fascinating work. Thanks for that. So the question I have is, did you take care to keep testing and training sets separate during the evaluation?
Yeah, so we split, as usual, the training and the test set.
So because in the example that you showed, I saw that for this lcrack example, you're predicting a method name that is called regexcrack. And I was wondering like how it would have learned that particular name if the training and testing are truly separate.
Yeah, so the tests are separate. We used all the binaries were Linux packages in our examples. So, and the only names that could be predicted are those that came from the training set. So we would have to look at this particular example and see from which binary it learned and why it was why this happened. But
yeah, because it's extremely specific and it's just a function name that exists only in this lab.
Yeah, I guess it was used in 2 different packages or something like that for this to happen. There's no other way it could have happened.
Hey, Dongpeng Xu from University of New Hampshire. Great work. I'm wondering, like in your work, the unit of the learning is a dependency graph, right? So I'm wondering how large is the graph? It's like a function or several statement?
Yeah, so the graphs have the size about 1 to 10,000 nodes. This is the size of the graphs. They get pretty big.
So every node is a variable.
So every node corresponds to it's different things, different program elements like variables, memory offsets, instructions, constants, types. So quite a lot of different.
And
different
the
kinds.
edge is the dependency, right?
Exactly. Yes.
Okay.
Yeah.
Okay. Thank you.
So, quick question: have you considered that the malware samples that you are using are statically including some libraries, like open source libraries, that you may have in your training data? Because it's clear that like malware, they don't want to depend on libraries, so it could have the case that you are in fact having the same on this set.
Yeah, that's a good question. So actually, the point is not to exactly predict. Usually, you don't want to exactly predict what was there. You want to capture. In fact, there are many systems where they handcraft some rules on, for example, that if you have a counter, you want to call it I, and so there are some standard rules of how you would want to predict some of the names. So here the point is to capture these cases automatically, so you can think of it as automatically inferring all these rules. So you can still capture meaningful names, even if they're not exactly the same that were written by the attacker who was writing the malware, but it should still be helpful to understand. So in a way, actually, these results, they provide a lower bound because we only consider correct only if it's actually equal to the original name or type. But in reality, you don't need this. You just need anything that's meaningful and helpful for reverse engineering.
Okay, but you have not used like a tool to check if the code was copy and pasted inside, like these clones, tools that detect clones in.
We have not. That could be one application. You could look at that.
Okay.
Yeah.
Thank you.
Yeah.
Therese Kroes, University of Amsterdam, or Free University, I should say. Thanks for the talk. I really enjoyed it. If I understand correctly, you use some set of rules, these 23 rules, to turn instruction streams into feature factors. My question is, how dependent are these rules on the compiler that was used to generate the code? Are they at all dependent? And as a malware author, could I choose to make my compiler maybe like analysis aware to fool your analysis?
Yeah, good question. So the rules are defined on an intermediate representation. So we use the BAP intermediate representation to extract the features from, and that's why it's actually pretty easy to get to support any compilers, anything basically supported. So we're kind of at the higher intermediate representation of that. I don't know if that answers your question.
Yeah, well, kind of. Do you know, like where all of the training set packages compiled with the same compiler, for example? Do you have some numbers on this, on maybe using different compilers?
So we compile everything as basically we use the standard makefile that's for compiling. So this included whatever compiler they have, including some of them had optimizations turned on. So we kind of disregarded this and said whatever way you used to compile, we're going to train on this using the intermediate representation.
Thank you.
Xiaorui from the Chinese Academy of Sciences. So my question is for the type recovery. Does this method works for the struct recovery? Do you think?
Yeah, I think that would be the next step, basically, to go to that level.
I want to know, do you think how accurate it will reach for the struct recovery?
Yeah, it's hard to say because we haven't done it, but I think that's a natural next step to basically start predicting more and more semantic representation from the binary.
Okay, thank you.
Yeah.
I have a very quick one. So I know that I'm keeping you guys from lunch, so I'll be very quick. So it's probably a follow-up on the previous or the second to last previous question. So have you guys experimented with different optimizations levels? So I understand that you use the standard one, but does your template in a way is agnostic, or is it affected, and how much is it affected to different optimization levels?
Yeah. So we actually did such an experiment where we trained on different GCC with different optimization levels, and then predicting also across different optimizations. It turns out there's actually little effect, and that's why at the end we just trained on whatever there is. Yeah.
All right. So if there are other questions, let's thank the speaker once again.